Okay, this video is for chapter 5.3, looking at the electrochemical series to help us predict if a mixture, the chemicals in it, what's going to happen spontaneously, a galvanic reaction. Pause it and look at what we're doing on the different slides. First thing that we're doing is you have to make sure your data booklet is set up so each of the reactions can undergo reduction. So reduction's the forward reaction, so actually write this on your data booklet. The back reaction is oxidation, so actually put this in your data booklet. If you pick an oxidation reaction, so if you want the aluminium to lose its electrons, when you write it out, remember oxidation is written this way with the electrons on the other side, so actually pick it up and turn it around. All of these chemicals on the left are oxidizing agents, and as you go higher and higher, they get stronger and stronger oxidizing agents. This is not the entire electrochemical series. I've cut the top off it here a bit. So on the other side, all of these chemicals here are reducing agents, and as you go lower and lower and lower, you get stronger and stronger reducing agents. This slide is about the idea that there's a few chemicals that are repeated in the electrochemical series, so you need to make sure you can identify where all the hydrogen ions are, the hydroxide ions, the water, the tin, and the Fe2 plus ion. So if we have a look, so I've cut the electrochemical series in half, so this is the top half. We've got water as a reducing agent here. Further down we've got water with oxygen, so this reaction won't happen unless you've got the oxygen present as well. And then further down there's just plain water by itself. So there's 4 waters, then there's hydrogen ions, 3 of them, 4 of them, and there should be one more up here, this one. This is our standard half cell. Okay, then there is hydroxide ions. So we've got hydrogen ions. If it says acidified, that's what you're looking for. They're the equations that will work, and if it says it's an alkaline solution, then you've got the hydroxide ions. So we've got tin, if SN2 plus as a reducing agent, and we've got tin as an oxidizing agent. We've got Fe2 plus ion, ferrous ion with the 2 plus charge as a reducing agent, and we've got it over here as an oxidizing agent. Alright, the electrochemical series with a mixture. Will a reaction happen? Is a spontaneous reaction going to happen? And what will the reaction be between? So you have to, everything that you've got, you need to identify. So write down all the different things in the question that could be possibly present and find them. Make sure if it says iron, which iron are you talking about? Because there's lots of the same sort of thing. So is it iron metal or one of the iron ions? Water. So the way that you know you've got water is if you see the word solution or aqueous. If it says it's an acidified solution, then it means it's got hydrogen to be an acid, or hydroxide or alkaline or something to have hydroxide ions. So the strongest oxidizing agent will react with the strongest reducing agent first, if they are of sufficient strength, so if the concentration is correct, because the electrochemical series is all based on a 1 molar solution concentration. Alright, so in this case we've got bromine ions and chloride ions, and aqueous means the chloride ions are dissolved in water. So find the chloride ions, the bromine ions, and the water. There's a water up here too, which I haven't bothered to circle, and there's water down here, which I haven't bothered to circle, and this one's not, because there's oxygen. So after a while you get used to the idea that you find the highest, the strongest oxidizing agent. So you work your way up And then all the ones underneath are relevant. It's the strongest one that's going to react if a reaction is going to occur. Same with the reducing agents. You work your way down the list so until you get to the one that's the lowest, the strongest one. So the water is the strongest reducing agent present, and the bromine ions are the strongest oxidizing agent present. These two are not in the right format. This is not strong enough oxidizing agent. It's not as strong as oxygen, so it's not going to steal the electrons off the water. Okay, it's not strong enough to react with the chloride ions or the water. I need to change this to water. So if we look at the next one, we've got silver ions and nickel. So the silver's here and the nickel's down here, and I've moved it a bit. So this is in the right orientation. The silver will undergo a reaction and force the nickel underneath it to give up its electrons. So the reaction between silver ions and nickel metal will occur because this is a strong enough oxidizing reagent. It's stronger than the nickel, so it will cause the nickel metal to oxidize. So they're the two half equations. Remember, pick this up, turn it around, and you get the nickel ions. Okay, which of the following metals would be coated with lead metal when immersed in a solution of lead 2+ ions? So our lead 2+ is down here. So it would get coated with lead if we had something underneath that's going to react with it. So we've got copper. Copper's up here. Gold is way up there. Tin is down here. And then the other option was none. So the tin is a strong enough reducing agent. The lead 2+ is a stronger oxidizing agent than the tin 2+. It wants electrons more than the tin. So if the tin actually has the electrons, it will force the tin to give it to them. So a spontaneous reaction will occur, so you'll get tin losing its electrons and the lead metal being formed. Okay, you can see the arrows cross over. That's another way of working it out. Okay, a steady stream of oxygen. So we're looking for our oxygen. So you have to find all of the things, actually, when we're reading the question. Find all of the things that are present. So you've got oxygen. Oxygen's O2. Chlorine is Cl2. The gas. It's acidified, so we've got hydrogen ions. It's in a solution, so we've got water. And you've got magnesium ions and chloride ions. I don't know, oh yeah, I have written the chloride ions. Yeah? So you've got a lot of things to find. Okay, so oxygen, and it's acidified, so we've got the hydrogen here. And chloride, chlorine ions, chlorine molecules, oxygen molecule with more hydrogen, oxygen with water, and our plain water, and there's nothing else. There's no other reducing agents present. Alright, so as you work your way up, the strongest oxidizing agent, which is chlorine, is going to react with the, work your way down, the strongest reducing agent, which is water. I've just written here, I didn't bother showing the magnesium ions down here, magnesium ions right down the bottom, because they're such a weak oxidizing agent, they're not even in the race. Okay, so the chlorine and water are the only two that will react spontaneously, naturally. So chlorine's going to get the electrons. Remember, we have to pick this up and turn it around, so the water's going to lose the electrons. If we put these two half equations together, you've got 2 electrons being needed here. 4 electrons being given, so you'd have to double the first one, first reaction. So when you put them two together, after you've doubled this, you'll end up with all the reactants on the left, all the products on the right, and you can cancel out your electrons to tidy up your equation. That 1, 2, you could put the hydrogen and the chlorine together to make 4 hydrochloric acid molecules. Which of the following metals would react when placed in water? Lead, zinc, or magnesium? So water, we've got lead, zinc, and magnesium. By now you should be getting used to the fact that the metals are all on this side. The metals all give up their electrons. So we've got our water over here, just plain water, and then you've got zinc, magnesium, and leads on the top there. Okay, so we want the strongest oxidizing agent, and water is the only oxidizing agent mentioned. And then we want the strongest reducing agent. So these lead and zinc, if you put them into water, according to the electrochemical series, there would be no reaction, nothing would happen. But if you put magnesium into water, it will lose its electrons, become magnesium ions, and the water will gain the electrons, become hydrogen gas, bubbles, and hydroxide ions. So only magnesium. So if we write a balanced reaction with this, we're going to have to put this and turn that around, put it together. So magnesium metal's oxidizing, the water is reducing, we've got 2 electrons on each side, so we just have to collect everything on the left, all the reactants, cancel them out. In this case we've got magnesium hydroxide, magnesium ions, hydroxide ions. You can put the two together and write it as magnesium oxide aqueous. Okay. For spontaneous reactions, water will react only, like we just did, will react with magnesium, will react with all these metals underneath it spontaneously. So if you put manganese into water, aluminium, magnesium, sodium, calcium, potassium, lithium. Okay. Obviously iron will react, but iron is reacting because there's water and oxygen, which is a higher oxidizing reaction up here, water and oxygen. So would calcium metal be found in nature? No, none of these metals would be found in nature. They'd always react, give up their electrons to the water, because the world is full of water. Okay, pure gold is one of the few metals found in nature as a metal, just a metal lying around. Why is that? So symbol for gold, it's Au. It's an exceptionally strong oxidizing agent, it's way up the top. So it's going to steal electrons from every single other chemical here underneath. Except the only things that would so it would steal electrons and become gold, and for it to give up its electrons and give them to something, it would only give them up to a stronger oxidizing agent. So fluorine and hydrogen peroxide are the only two oxidizing agents strong enough to get the electrons from the gold, and seeing as fluorine and hydrogen peroxide are strong oxidizing agents, they would have reacted and you wouldn't find them in nature. Is it possible for hydrogen peroxide to undergo a reaction with itself? So if you look on the electrochemical series, you've got hydrogen peroxide here, and it's in the right pattern. What would the voltage expected for the two half cells? So remember voltage, it's the difference between here and here. What's the gap between them? So if you take 0.68 away from 1.77, you'll get 1.09 volts. So that's the difference between them. So that's the voltage if you had a 1 molar solution. If this happened, you would expect gas bubbles at one of the electrodes. Which gas and which electrode? So if you have a look, you're making water here, and you're making oxygen gas here. Okay, this reaction is oxidation, isn't it? When you go in the reverse direction, it's oxidation. An oil rig cat. An oil, oxidation is the loss. So anode is where oxidation happens. So oxygen would be bubbling up from the anode. The anode is the negative electrode for spontaneous reactions. So they could have said what gas is formed at the negative electrode. In practice, though, you actually don't see the gas bubbles. Why do you think? So this reaction is so slow that the gas would not form bubbles which could be seen. So there would be small amounts that wouldn't actually collect to form a large bubble. They'd just dissolve in the water. Alright, equal amounts of oxygen and hydrogen will bubble through a solution of iron chloride. Write a balanced equation for the reaction that occurs. Does the pH of the solution change? So you need to identify all the chemicals that you've got. So you've got oxygen and hydrogen gas. You've got a solution. So you've got water, you've got iron, 3+ ions, remember, cross it over, and you've got chlorine ions. Okay, so find them all, circle them all. Okay, that's all of them. So if we look, strongest oxidizing agent appears at the moment to be iron, 3+, and the strongest reducing agent is the hydrogen. So the iron 3+ is going to get electrons from the hydrogen and turn into iron 2+, and the hydrogen is going to oxidize and produce hydrogen ions. So if we write them out, remember to pick this up, turn it around. So you always make sure that you've got electrons on both sides. We've got 1 electron here being required for reduction and 2 electrons being produced, so we're going to have to make this happen twice. If you put all the reactants together, you end up with this. Then we can cancel out the electrons on both sides. So that's the overall equation. Does the pH change? So our reactants, we're producing hydrogen ions. More hydrogen ions, does the pH go up or down? Think about it. Increasing the hydrogen ions, the pH goes down. Remember the pH scale? 7, 6, 5, it's acidic on this side direction. So as it goes from 7 down to 1, the concentration of hydrogen ions increases, so the pH decreases. Which electrode are they produced at? Alright, so hydrogen was undergoing oxidation. I'm not sure if I've got it written down. Oxidation happens at the anode or at the negative electrode, depending on what the question asks. Alright, if you change the standard conditions, so it's standard conditions 1 molar solutions, 25 degrees and 1 atmosphere pressure for the gases. So if you change the conditions, then normally the strongest oxidizing agent according to the electrochemical series and the strongest reducing agent will react first. But if you change the conditions, then the order that we have them written, they might change. So instead of being in that order, they would be in a different order, and in that case then different things can react. Okay, a student is planning to set up a demonstration of organic sample using half cells constructed as follows. So read the question. Calcium electrode in a beaker containing aqueous solution of calcium ions. A platinum electrode, platinum is inert, doesn't react, in a beaker containing a solution of a mixture of tin ions. And then he's put the salt bridge between. The electrode would be attached to a voltmeter. This particular cell is impractical. You wouldn't really set it up. Why would you not put these two half cells together? Can you see any point? Look on the electrochemicals. Any problem? So these are the options. Just pause it, have a think. Which one of those sounds like the problem? Okay, it's the first one. Solid calcium, when you look on the electrochemical series, will actually react directly with water to form hydrogen gas. So solid calcium, in fact any of these metals, will react with water to form hydrogen gas. So you're not going to get the electrons going through the wire if you set up these two half cells. The half cell itself is having a reaction. Alright, in which one of the following sets of substances are all of the members of the set able to undergo a spontaneous redox reaction with pure water? Pause the video, have a little look. Remember there's a 4 water. Okay, if we look, there's B. I'm not sure if the slide. No. So the fluorine is up the top and it reacts. It's in the right spot for the water over here. The water over here, when you look down, you've got magnesium underneath it, and the gold is the same as the fluorine. The gold and the fluorine are above the water as a reducing agent. Which of the following will be predicted to spontaneously oxidize water, iodide ions in water, but not react with chloride ions in water? Which one of the following here? So we've got iodide ions and we have chloride ions. So we want something that will react with this but not react with this. So clearly you're wanting something, an oxidizing agent, that one of these, but as soon as you get to one of these, then that will react as well. So I can't remember the options. I think it was this one. No, it's this one. So it's bromine, which was apparently the last one. Alright, a student investigating redox reactions records the following. So you've got this bit of information. You don't know what V, U, what they are. TE is probably tellurium, but you don't know. Let's pretend you don't know. Based on these results, the strengths of the oxidizing agents are arranged from the strongest to the weakest. So you have to put them in order of electrochemical series. So we need to put the one that's going to get the electrons right on the top. So in this case, it doesn't really tell us much. It's saying that there's no reaction, which basically means that the one that could get the electrons, in this case the V could get the electrons, it must be underneath the TE. So there's no reaction here. So for a reaction to happen, V2 plus is capable of getting electrons, and TE is negative, it's capable of giving electrons. So the V2 plus you would normally put up here, and the TE minus if there's going to be a reaction, but because there's not, then they must be in this pattern, V2 plus Te2 minus, like that. So which means the tellurium reaction is above the V. So we've got TeV so far. Then when we look at this, we can see that there is a reaction. So this is giving its electrons. This is giving its electrons to the U4 plus. And for it to give, it has to be in that pattern, which means that the U4 plus must be above the TE. Okay, so what was the question? Now that we've got the order, so we've got U, TE, V2 plus. So the question is, the strengths of the oxidizing agents arranged from the strongest to the weakest. So we want the strongest one to the weakest one. So the strongest one was U4 plus Te V2 plus U4 plus Te V2 plus U4 plus Te V2 plus. So it's B. Sorry about that.